My name is Frederic. I'm the head of the AI group at Samasource in Montreal. I'm going to talk to you about machine learning for computer vision annotation. So many of you may not be familiar with Samasource. We're actually a bit over 11 or 12 years old, but we started the office in Montreal relatively recently. So as you may have guessed, we are primarily an annotation company for computer vision, because of course, without training data, there's no AI, there's no machine learning, there's no computer vision. So you all know that. So what we do is really help mostly at the moment large clients, for example, Walmart, Google, Microsoft, IBM, and so on, create more accurate models by helping with labeling data of various kinds: images, videos, key points, LiDAR, and so on. We've annotated around 1.5 billion points in 2020 so far. So we have very large teams, which I will mention in a few minutes a little bit. Yeah. So this is all done via our platform, which is called the SamaHub, which is a web-based application for large-scale annotation projects, which include task management, workforce management, quality control. We have an analytics platform. We have various APIs. We also have impact tracking, which I will also mention, because at the core of Samasource is really impact on workers, impact on annotators. And yeah, various ways that we can specify data project configuration for each customer. All right. And we deal with multiple media. So 3D LiDAR data, which is very useful for self-driving vehicles. We have video object tracking. So you can see we have some interpolation going on here. We have a bounding box that's following the car here. So this is interpolated automatically. We have semantic, vector segmentation, polygons, sensor fusion. I'll come back in this presentation to polygon specifically, and a little bit sensor fusion. I want to present you a little bit some projects that we've been doing in machine learning. So before, I'll just describe a little bit more of the company and what we do. We work with multiple industries. So autonomous vehicles is a very big one, one in which we have some years of experience. E-commerce, retail, you've seen Walmart, for example, in the list of customers. Communications, smart hardware, biotech. So yeah, we have mostly large enterprises. We're taking also medium-sized companies, and we're looking at taking smaller ones. But yeah, we're working with all of these industries at the moment. And finally, about the company. So beyond the SamaHub, beyond the annotation platform, Samasource was founded as an impact sourcing company with the goal of improving the livelihoods of people coming from underserved communities through training and through employment opportunities. Because, for example, Nairobi is one of the locations where we have our largest annotation office. We mostly recruit from a slum called Kibera, and there's a lot of people who have education, but there's really not a lot of opportunities there. So what we do is we have various programs to teach computer skills, and then most of these people end up employed on our payroll, and they work for annotation. And we have some programs also to fund sometimes those people go and start out some companies on their own, and with the help of our investors, we've been able to fund some of those initiatives, for example. So really, the social impact and the social mission is at the core of what the company is about. And yeah, this started in 2008, and we did a longitudinal study, and we impacted about 52,000 workers and their dependents. So yeah, just to give you an idea, this is the map of our locations, but the annotation offices, delivery centers, are mostly here in Gulu, Kampala, and Nairobi, so in Kenya and Uganda. The rest of our offices, so Montreal is mostly about tech. We have San Francisco, Tres Rios in Costa Rica, and The Hague. All right. So moving on. So this is a little bit about what is Samasource, who we are. I will go to the heart of my presentation today, which is about machine-assisted annotation. So I spent a great deal of time, a couple of minutes describing the various types of annotation work that we do. So now you may ask, okay, why machine learning? Where does that fit into that? Of course, we provide data for machine learning, but do we do something on top of that? Well, the answer is, of course. Just so that we align on the terminology, I know you're all familiar with these problems, but what I'm going to focus on in this next section is mostly semantic and instance segmentation, where in the case, for example, of semantic segmentation, we have a scene. We want to say, okay, this is grass, this is some forest, this is the sky, this is a cat. Or in the case of the instance segmentation, we want to identify and draw a mask around each of the objects in the picture, in the image, that are part of the categories that we care about. So here, for example, a dog and a cat. I won't spend much time on object detection. We have a lot of object detection projects, but there's not so much that we can do with machine learning to improve that, because if an annotator, for example, needs to adjust the bounding box, for example, you're not saving a lot of time over just drawing it from scratch. So what we've been caring about most so far in terms of machine learning really is semantic and objects and instance segmentation. A typical example of that kind of data is an urban scene here with vehicles, with cyclists, with roads, and so on. So semantic segmentation will produce a mask delineating each object in the scene in the case of instance segmentation, or just the general categories for semantic segmentation. This is very useful for most, all self-driving projects requires a lot of labeled data with that kind of segmentation. So we have a lot of clients that are asking for such data. Now, why machine learning? So annotating those images and those videos manually is really time consuming. Machine learning can help by automating some of the tasks that can be learned by a machine. For example, here you don't necessarily need a human to say that this is orange and this is yellow, and these are shapes that are pretty easy to segment. So humans are still required to verify and adjust the machine's output, because you may ask, well, if your social mission is about training and employing people, why do you want to automate them? We don't really want to automate them. It's more about taking on more customers, increasing the pie, and making sure that the company is competitive with the others and can sustain its model of employment. So specifically for instance segmentation, there's been many machine learning methods that have been suggested to speed up the process. I'm thinking mostly about few-click annotation methods like Dexter, for example. So this is actually the Dexter paper, which what we did here is re-implement that paper, and we did some modifications, which I will describe. It's a paper from 2 years ago from ETH and Zurich, and you can see how it works here. You have the user that's going to input the extreme clicks around the object, and the algorithm is going to find a mask. So this works. This is class agnostic as long as you've seen those classes in the training set. So you can see here the car, the cyclist, the bicycle, and so on. Typically, these are not tested. As for most machine learning papers, these are not tested in a production environment where you need a high quality. So this is something that we really have to benchmark, because in papers you'll see, okay, this is 80% or 90%. Well, this is good, but it's not always enough. So one thing that we found is that if you use machine learning for annotation, you need to have a model which can output something that is easily workable by a human. You can't really, if you output like a raster mask with a million pixels, it's really cumbersome to edit for humans, so you're not really saving that much. This is the SamaHub. This is an internal data set. It's not very good data. It's a bit pixelated, but I can't really use customer data here. So typically, if you let's say the task here is to annotate the cars, the vehicles. Typically, what an annotator would do is take the polygon tool and then start and click like this. It's kind of a little bit annoying, and And actually here, this is really crappy. It's really low quality. So normally they would need to go really around each little part of the object, say like the vehicle. So what we try is to improve upon that. So I'll just remove that, and we introduce this Dexter tool, which enables you to draw a mask just based on the extreme clicks. All right. I'll come back to this demo just to show you how to edit. But this is the crux of it. How it works is we've modified the Dexter paper, but actually in the paper they use a fully convolutional neural network. We just replaced that with our own implementation of a UNet, which is more lightweight, which we call the Sama UNet. So the annotator will select the 4 extreme points around the object. It will create a heat map around those user input at inference time, and then concatenate the heat map with the input image. Now we pass this through this model and we obtain a raster mask. The problem with raster is that it's pretty, it's not really easy for the annotator to edit. So we have also an algorithm which takes the mask and outputs a sparsified polygon. Now this is quite important because you don't want your polygon to have like 1,000 points, otherwise it's really hard to edit. So you want to focus the density of points where the curvature is maximum, for example. So this is something we've experimented with a lot and came up with something that was more or less optimal. So the message here is that IOU, the model IOU is very important, for example, but what's also important is the editability of the solution for a human in this context, if you have such a human in the loop system. All right. So here's an example. These were at the top were annotated manually, at the bottom annotated with the few click method. The IOU is pretty much the same, and you can see that the drawing patterns are quite similar because it's the automatic method is based on curvature. All right. And just to give you an idea of the potential gains, we run an A/B test on this toy data set. This is not a real data set. This is called CAMDEA. If you want to play with it, it's a synthetic data set. It's free for research purposes. We've observed on an A/B test some gain of up to 3 times the annotation time. Well, 3 times less the annotation time. We've applied this to a project. We didn't observe that kind of gain, of course, because in a real project you can have 30, 40 classes, and we haven't trained the model yet on all of those classes, but this is something we've introduced. All right, I'll go back to my demo and I'll show you something else. So let's say you're not really happy with the boundary, and you want to edit this. You're like, oh, maybe I should move this here. This can also be quite a long process. So we've also introduced a smart editing tool. So instead of editing manually, you just move a point or add or delete one, and the model will do an additional inference based on a 5th click or potentially a 6th or 7th or 8th click, every time refining its prediction based on the additional input. So this is something we also just introduced. And the idea is that Dexter, the 4 extreme clicks required by Dexter are not always sufficient. So what we did is to sample hard examples and add an additional click during the training time, so that at inference time, the model could deal with a 5th, 6th, or 7th click if the shape is complex enough so that this is necessary. Oh, there's a question. The synthetic data set, it's called CAMDEA. I'll just write it in the chat. All right. So that's it for that. We carried out some experiments with that as well. And again, we reproduced the three times result with the 4 clicks. And with the 4+ clicks with the smart editing tool, we can go and have some additional gains as well. So we observed up to 3.5 times faster. We also applied this on some real projects. The gains, again, were smaller, but we were still observing a lot of gains thanks to that method. And A/B testing is really at the core of setting up those kinds of methods, because a method in a paper can very well say, okay, this speeds up annotation by 10 times. but then you end up in a real project with really weird guidelines and things you really have to work around, and it's not obvious that something is going to be actually helpful to humans. So you need to be A/B testing stuff all the time, and this is what we've tried to do to get to some real world gains with in the production setting. All right. So that's that for the what I wanted to present as the main project tonight. I just want to say a few words about some other thing that we started to work on, which is called sensor fusion. So this is an example of 3D annotation that our annotators do on our platform. So this is data coming from a LiDAR. It's one of the sensors that are on top of self-driving cars, and it outputs some point clouds of where the light has reflected on the various surfaces. It's a really complex annotation task because what clients usually require is a cuboid around each of the shapes. The shapes are not always visible. This is actually a really nice point cloud. Very often it's much less dense, and you have to guess where the objects are based on like 5 or 6 points, and it's really difficult. So we have multiple views here to allow the adjustment of the cuboid, and in fact, it needs to be very tight. So this kind of, if you have a video with 200 frames, this is something that can take multiple days to annotate. It's crazy. So what we're trying to do is to use machine learning to speed up that process. It's not obvious because we need to get to a very high accuracy. We need to get a detection in the 3D space that is very tight. So what we're trying to do is to use multiple sensors. This is why it's called sensor fusion, to use information from multiple sensors to arrive at a better prediction. This is not as easy as it sounds because in fact, the data from the multiple sensors are not always aligned. They rely on multiple parts of the car, for example. And we've actually built a model to do this alignment, and it was an effort of several months. And now we're looking into, for example, combining 2D object detection with 3D clustering in order to come up with some method that allows a really accurate pre-annotation of 3D cuboids.
Um, Tell us again just for a little bit, because I love the fact that Samasource are kind of really trying to do some social good. So to talk to us a little bit about more what's happening there.
About the impact.
Yeah.
So basically, what we're doing is to provide. We work with various consultants with various sources of data to provide living wages, fair wages, to our annotators. They're not contractors; they're on our payroll.
Mhm.
And the difference, you may ask, how is that different from just normal outsourcing? The original idea was to provide work. When this was started by Leila Jana in 2008, the idea was just, okay, can we find some work to do for people who live in slums or just underserved communities who may actually have sometimes a university education, but they have to support their family, and they don't really, there aren't really any kind of
Options
jobs
for
over
them.
there, because social mobility kind of works once you've reached the kind of middle class. But for all the communities that are below that, it's actually very hard to move up. So the idea was just to find some work that they could do. And with time, it has morphed into a full-blown annotation company. But I would say the main difference with the normal outsourcing is really the communities that we target in order to have the maximum impact on people's lives, and the fact that we monitor the impact that we have on communities. We just had a paper published with a group at MIT on just a multiple year study on various control groups, and which part of those populations have moved upwards the most, based on whether they had the training or not, whether they had been employed or not, and so on. So we do actually care about whether we really have an impact, and we try to assess it using using external observers.
Yeah, no, that's great. I have a lot of respect for businesses, trying to do some social good in the world. I think often tech, especially, have all these the Bezoses of the world who could literally like just insane amounts of wealth hoarding, and I think it's great to see tech businesses really getting involved in, as you put, those underserved communities. So way to go, Samasource, for that gold star for helping the community there. It may sound a stupid question. We don't have stupid questions at CAMDEA, actually. We just have questions, so don't worry about
Indeed.
that. If Sumer, UNet, and Dexter does good work, why limit it to annotation? Can it be also used for segmentation directly, i.e., instance segmentation at the production level?
Well, the Dexter approach is based on the fact that you have user input. The reason we do that is that having user input allows you to get just a much higher accuracy than what you would get using just fully automatic instant segmentation. So the idea here is that we have humans that can do work. So what work can they do that can improve maximally the model accuracy in the most efficient way possible? So yes, the Sama unit could totally be used for pure instant segmentation without any kind of user input. But the whole idea of having Dexter is leveraging user input to improve the accuracy of the prediction.
Very good. And we got a question from Eric. Eric has asked, when you do A/B testing, how do you control for the inflation of type 1 error through multiple testing? And then he's put in brackets, I would imagine that you are doing many tests for each research question in this type of work.
Well, how we would typically set up an A/B test is that, for example, we ran one on a production project recently. We've just split a data set from a client, for example, and on one hand we would have a team of annotators just working manually. Then on the other branch we would have a team of annotators using the feature. Now at the end of the process, there's QA. So if something is if we're missing objects, or if we've annotated objects additionally that shouldn't be annotated, this just goes back to rework. What we call rework is just the task is sent back to the queue because it hasn't passed QA. So given the QA process, we assume that what has been annotated in terms of, okay, what's the precision, what's the recall of the objects that we found, we assume that this is taken care of by the QA, and that therefore it's kind of equal.